Hello everyone, today we're going to talk about diagonalization, which is a really hard word to say, but a very useful concept to know. So in the last video, we talked about similar matrices. So we say that if we can find this linking matrix that's invertible, that's called P, that links A and B are said to be similar. And if we know two matrices are similar, we know they have the same rank, the same trace, the same determinant, the same eigenvalues. We can extend that and say that A is diagonalizable if and only if it is similar to a diagonal matrix, i.e., instead of just having any matrix B, we say that the matrix on the left-hand side, D, must be equal to A times P. We say that we can find this linking matrix here called P inverse, and we can link it in such a way that we get a diagonal matrix on the left. And that's where the diagonalization comes from. And if we want to write it in another form, we can also multiply by P on the left. So we get PD is equal to AP. And then we multiply by P inverse on the right, so we can also say that A is equal to PD P inverse. But why are we even interested in this diagonalization in the first place? Well, for one, it helps us efficiently compute matrix powers. So matrix powers. Because if we have a diagonal matrix, let's say we have the diagonal matrix A and B, just like this. And if I take the square of a diagonal matrix, for example, if I do D squared, well, that's just going to be A0, 0B, multiplied twice. And since kind of this column right here just picks out the first column right here, we actually see that we're going to get A squared 0, B squared. So actually, the D to the nth power, if we say that A is first here and B is second there, we actually know that D to the nth power is going to be A to the n or B to the n. So it makes computing the powers of a diagonal matrix is pretty straightforward. We just take each original entry to the nth power. So then, if you know that A is equal to all of this business up top right here, if we do A to the n, that just means that we're going to take all of these things right here and we're going to multiply it n times. So we're going to do all of this right here. We're going to do that n times. But since P is invertible, and that's the key here, at all of these junctions, when we multiply them together, this is just going to cancel and become the identity matrix. All of these things. And that means that instead, we're only left with these D matrices here in the middle, getting our matrix power. So in the end, we're actually just left with P, D to the n, P inverse. So if you knew the original P and the original D, you just take every diagonal and you raise it to the nth power, and voila, you have A to the n. And why do you even want to have the matrix power in the first place? Well, you could imagine working with Markov matrices. Because often there, we're interested in how something changes over time. You have a transition matrix like 0.3, 0.7, 0.2, 0.8, and then you want to say, okay, how does this change if I take this 10 steps or 100 steps or maybe even infinity amounts of steps? And converting A to a diagonalizable form will help us find these powers much more simpler. And it also comes up when solving differential equations. So solving differential equations. Because when we solve differential equations, a lot of times we're going to have e to something. And often when we're working with matrices, we're going to have e to some matrix. And the definition of e to some matrix will involve kind of an expansion, a Taylor expansion of matrices, where we kind of say it's the identity plus A squared over 2 plus A cubed over 3 factorial and so on. And here, again, we're taking the matrix exponential. So diagonalization really helps us in these cases. And finally, it lets us find inverses. Inverses, if they exist. Because let's say A inverse exists. If I know that A is equal to P, D, P inverse, if I then take all of this inverse, it's going to be P, D, P inverse, inverse. I'm going to shift everything around. That's going to be P inverse, inverse, D inverse, and then P inverse. So all of this is going to turn out to be P, D inverse, P inverse, which looks a lot like what we started with originally, except that we have this pesky D inverse. But it turns out if we're diagonal, like if we have an inverse, D inverse is just going to be all the original diagonal entries, but just 1 over them. So this would be the D entry in the 1, 1 position. All of these things are kind of 0, and then all the way down to the kind of DNN position, if this diagonal matrix is an n by n matrix. Once we know the inverse, it will help us solve systems of linear equations. For example, if we know ax is equal to b, we want to find what is this x vector right here. Well, we can multiply by A inverse on both sides. And voila, we can kind of find our x right there. So diagonalization really is key to a lot of these operations, makes them a lot more helpful. But we can then dive deeper into what is this D? How do we even find this D and this P matrix? Where does it all come from? And what's really cool is that actually D must correspond to the eigenvalues of A. D contains the eigenvalues of A, and P contains the eigenvectors of A. And why is this the case? Well, we can start with our definition. We say that D is connected to A by this special matrix P. And if I multiply by P on the left, we can see that we get PD is equal to AP. Now, we can expand each of these. So, for example, for my PD, because we said that PD looks something like this, where we have like D11 all the way through DNN, and all of these things are zeros, and our P matrix is just kind of, if we think of it as columns, it's just going to be like P1 all the way through Pn, like this. When we're taking the matrix multiplication here, we can actually see that we're going to take this column right here, we're kind of going to pull it atop. So this is kind of what we're doing when we're doing our matrix multiplication. So we're kind of going to put this right on top, and then we're just going to go down, and we can actually see that D11 is actually just going to impact our first column in our P matrix here. We're going to multiply each component of the P1 vector by the first diagonal entry. So actually what this ends up looking like is something like this. D11, P1, all the way to DNN, Pn, right? So we're taking the diagonal entry and the corresponding kind of P vector right there. Then finally, we can look at AP. So AP, and AP, again, we're going to have the matrix A times this matrix of all the way to Pn, the vectors or the column vectors of P. And again, we're applying P1 and Pn to A. So we can actually just write this as saying, okay, apply A to P1, and then that's our new column. And then apply A to Pn, and then that's our new column. But we know these must be equal, right? PD equals AP. So that means that these two things must be equal. They must line up. So we get this thing, that AP1 is equal to D11P1. And this holds all the way until APN is equal to dn n p n. And what does this mean? Well, this is interesting because we have the same vector on the left and the same vector on the right, and we're taking a matrix A, and we're connected with just a real number right here. This is just a number, this diagonal entry. And that looks very, very similar to our eigenvector equation, right? Where we say we apply some linear transformation, in this case A to V, we get it scaled by some number, but we preserve the V, and voila, it's actually the same thing right here. So that means that if we have this diagonalization rule, the D is actually the diagonal values are composed of the eigenvalues, and the P matrix is composed of the eigenvectors. Now, we often denote the diagonal matrix composed of A's eigenvalue, the kind of lambda, big lambda here, because, D kind of stands for any diagonal matrix, but in this context, because it corresponds to the eigenvalues of A, we often say lambda. And often when we do these P's, these eigenvectors, we often put them in a normalized form. We often make them what's called orthonormal, which means that they are orthogonal to each other, but also have length of 1. So each P vector, we're going to have a length of 1. And when we do that, we can say that the P matrix is also orthonormal, and then we denote it by X. So we kind of get this relationship right here, that X inverse AX is equal to this diagonal matrix called big lambda. And we can also then rewrite this just by multiplying on the sides with X and X inverse. And we can kind of put it in these two forms right here. And notice now what we need, like a criteria for this to work. Because X must be invertible. It must mean that X must be full rank, which means that we need to have n linearly independent eigenvectors. We must have n eigenvectors. So if A has a shape of, for example, n by n, then we need a full set of linearly independent eigenvectors. Because otherwise this wouldn't work. Otherwise we wouldn't have X as an invertible matrix. And this means that we might come up with a problem if we have less than n eigenvectors. It might be a problem when A is defective, because then we can't do all of this fancy stuff. If A is defective, we won't find the invertible X matrix. And in those cases, we have to go somewhere else. We need to find maybe not a diagonal matrix, but we're actually going to find the matrix J, which is called the Jordan form. And that will be the subject of the next video. But just to really hammer in how incredible kind of this form is right here, what this is doing, is that we can also reanalyze this. We can see the matrix transformation of A in new light. This X matrix here is often called a change of basis matrix. And why is that the case? Well, for that, we will need some more animations. So let's look at an example. So here we have the matrix A, and with diagonalization, we're going to re-express this transformation as a combination of rotation reflections and stretching matrices. So first of all, this matrix A here corresponds to the following transformation. So what happens here is that we're actually sending the basis vector E1 to 1, -1, so there's a green arrow here, and then we're taking the basis vector E2 and sending it to 2, 4. And then we can track all the other vectors in the space as kind of doing the same thing, that we're kind of going to get this rotation and stretching as we see here. And we can interpret then the first column, so 1, -1, really describes where E1 goes, and 2, 4 describes where E2 goes. Now, using the diagonalization, we first need to find the eigenvalues and eigenvectors of A. So in this case, A has the eigenvectors 1, 1 and 2, 1, and we have the eigenvalues of 3 and 2 respectively. And since we are eigenvectors, that means that even after we apply A, these eigenvectors are going to stay on the same line as we did prior to the transformation. Then we can package, as we saw, the eigenvalues in this diagonal form and the corresponding eigenvectors in the P matrix. We just find its inverse using our inverse formula, and voila, we have the diagonalization as follows. And I want to really bring your attention to this P inverse, because if we can interpret P, as we said before, as taking the basis vector, so E1 to 2, 1 and E2 to 1, 1, that means that P describes taking the basis vectors to the eigenvectors. But that means that P inverse must do the opposite, i.e. taking the eigenvectors and sending them to the basis vectors. And that is exactly why P inverse describes the change of basis for this matrix. We're changing the basis vectors to the eigenvectors. And then we're going to apply this diagonal matrix. And what a diagonal matrix do? They only represent scaling of basis vectors. So for example, 2, 3 is going to scale the basis vector E1 by 2, and then the basis vector E2 by 3. So first, we're going to rotate our eigenvectors into the positions of the standard basis vectors. Then we're going to scale them by their eigenvalues, just as we want. And then, crucially, we must turn the eigenvectors back to their original position so we can preserve our original basis, i.e. when we have the standard basis vectors E1 and E2. So that's what's happening here. We're changing the basis to an eigenvector basis, we're scaling the eigenvectors, and then we're rotating it back, changing it back to the standard basis. So all in all, matrix A can be a combination of these operations. We find our eigenvectors here, we rotate them to be our new standard basis vectors, then we scale them by the eigenvalues, and finally we rotate everything back to regain kind of the position that we would have if we would have used our normal original E1 and E2 basis vectors. So I hope that made diagonalization a little bit clearer why it is important. So if we have a defective A, i.e. we don't have enough eigenvectors to create this piece, that's when we'll need the Jordan form, and that's the subject of the next video. Thank you for watching.